So this is the methodology of what is called, is usually referred to as the seamless phase 2, phase 3 design. So it's the multiple looks combining p-values design, where if you select it, again, you can have, it's typically a 2-look design. So you have at the interim look, before the interim look, you might have a number of arms compared to control. And then at the interim look, you want to select either the best working arm or the 2 best working arms to move into the next phase to be compared against the control. So the way that you would, again, the boundaries, the efficacy boundaries can be in terms of an adjusted p-value. And then the treatment selection, you can select either the best treatment to move into the next stage or select the best 2 treatments to move into the next stage. And then when you have done that, you will be combining the results of the 2 phases with a combination function. So typically, you can use the inverse normal combination of p-values between the 2 stages to do this. And you can also use different multiplicity adjustments for the multiple arms that you have on the first stage, whether this is Bonferroni, the CDAC, SIMS, or the Dunnett parametric test.
We have stopping boundaries for efficacy and futility. The trial will stop the first time that any of these multiple arms crosses an efficacy boundary, or if all arms cross a futility boundary, it'll stop. But in addition, as you go along, look by look, you can drop the losers. So any individual arm that crosses a futility boundary can be discarded, and the remaining arms can keep going. You specify that you have 3 looks. You specify that you have 4 arms, and you want 90% power, and you can specify the means that I'm now designing for 3 means of 0.18, 0.18, and 0.18 with an allocation equally allocated, and a sigma of 0.5, and then I can press the compute button, and I'll get the output which I've saved over here. And this output says that now I need 130 patients per arm rather than 165 per arm for the 2-arm case. So the question is, why do I need fewer patients per arm when I've got 4 arms compared to 2? Well, there's more chances of crossing a boundary if I've got 4 arms instead of 2. On the other hand, the boundary has got to be stricter, because under the null hypothesis also I've got more chances of crossing that boundary. So then next thing to do is you ask yourself, well, let's look at the boundaries. What do the boundaries look like for these 2 different designs, one which is a 2-arm design and one which is a 4-arm design? So here you can see this 3 equally spaced looks. This is a classic O'Brien-Fleming boundary for 3 equally spaced looks with a z statistic of 3.7, 2.5, and close to 1.96. An O'Brien-Fleming boundary is pretty conservative. At the last look, you spend some alpha along the way, but it's very close to 1.96. Not so with the 4-arm trial. Now the final criterion is much stricter. It's almost 2.4 in order to preserve the type 1 error.